From this 3D model, it was possible again to create this mirrored version of the model and to compare the original and the mirrored version. And I did it for all the three sources of data. For this area, this corresponds to 572 cubic centimeters per hour.
That's a little bit crazy.
You think? If we recompute it, we will get to 443 tons, which is approximately 73 elephants or one Boeing 747. The inside points of the cut and the starting and the ending point of the cut are on one line. So the inside of the cut is linear. It's not circular. If you go deeper, it will be sharper. So yeah,
That's what she said. Marián Marcis, thanks for accepting this invitation finally.
Finally. Yeah.
Cheers.
Hello,
to that.
hello, Carolee. Nice to see you again.
Nice to see you.
Meet you again.
We have been working together for, I think, 1.5 years now.
Mm-hmm.
This is the second time we met.
Cheers to the technologies.
Yeah, what I wanted to say is that it's funny that you can work together with someone for such a long time. It's not a long time, but if you think about how many messages we exchanged and emails and ideas, but we never met before that. We meet after 2 years of collaboration, etc. It's yeah.
Yeah, we are working on very similar things. So yeah, we have a lot of common, I think. So
yes, I met your work first time on X.
Mm-hmm.
After I returned from Egypt. I was on a tour in 2024, and I did some basic photogrammetry stuff with Luma AI on my phone, and I was scrolling on X, and I saw the Ramesses head scan have been analyzed, and I was like, "Huh? It seems like my scan, but." You had different scans from different sources.
Yes.
And one of them was I mean, on one of those scans you wrote that Luma AI, and I knew that probably that's mine. And actually Adam Young, who was also on the trip, asked this scan from me if I can send it, and he sent it over to you because you knew already each other. So that was the first time I saw your work on X, and I think it was very impressive how many different stuff you analyzed and the details, and also I think the conclusions will be also interesting at the end of this show. But I was like, okay, this guy is very cool, and also the work was very detailed, and I like the idea how you wanted to approach these kind of old mysteries, relatively old mystical questions of the ancient times from a modern perspective and from the modern point of view, and applying new and modern technologies on these questions. But please introduce yourself and let us know what do you do exactly, and what are your credentials.
Okay, thank you for the introduction, and I will say a few words about me. First of all, I would like to apologize for my English to the viewers.
So
I'm not a native speaker.
Just to let them know, it took, I think, 1 year to convince Marián to speak in English on this show because his mother tongue is
it's
Slovakian.
Slovak, of course. I'm Slovakian. Yeah.
And he thinks that his English is not good enough to have a technical conversation, but I think that's not true. We had a lot of good technical conversations together so far, and I think this will be a very impressive and good show. So don't be afraid of that.
So let's go to introduce myself. I am a surveyor. with a specialization in photogrammetry and documentation of cultural heritage, where photogrammetry is very often used. I am working on the Department of Surveying at the Faculty of Civil Engineering, Slovak University of Technology in Bratislava. And I have my master's degree from 2009 in the field geodesy and cartography. The PhD was in 2013, and after a few years, I got also the associate professor title. So I am a scientist and I am a teacher, of course. And I teach not only photogrammetry, but mainly the basic geodetic subjects.
Are you the new Flinders Petrie?
I don't think so. He was definitely a polyhister, but yeah, he was also a surveyor. So of course I know him from this side too. Yeah, of course. But it was always amazing about these old guys in a few hundred years ago, that they were professionals in so many fields. They were historians, archaeologists, surveyors, astronomists, chemists. Yeah.
Many polyhistors, yeah. I think you had to... These guys achieved a lot of things, and I think that was the reason why, because they were good at so many things at the same time.
Yes. They could connect the dots, maybe. Yeah.
And bring a new perspective. I think Petrie was also very famous because became famous because he brought a completely new perspective. He brought the scientific methods for documenting the stuff in Egypt, and it was not very done before him. So he could bring this kind of new science into this field.
Yeah, that's true. Yeah. What should I say more about me? Maybe why
Why are you scanning and photographing rocks?
Yeah, that's a good question.
What's your initial motivation, or how did you start this topic?
Yeah. Well, I was always interested in this ancient stuff in ancient Egypt. Not only Egypt, all ancient cultures, of course. But everyone starts in Egypt. I think there are the most mysterious, amazing monuments, artifacts, and I read a lot of books about ancient Egypt. But it was first 4 years ago when I was able to visit Egypt personally for the first time. So I would like to express my gratitude to my wife for letting me travel there with my friend, Martin Kosha. He was also a surveyor. He is a surveyor too. Yeah,
dangerous trips.
Dangerous trips, yes. It was a man's trip, not a family trip, definitely. We actually started the trip with sleeping on a bus station on chairs
in Egypt.
In Egypt, in Hurghada, because the flight arrived at the midnight, and we had no accommodation, and we just wanted to wait for the first bus to Luxor, so we slept on the bus station.
But that's even a long ride, 4-5 hours.
Yeah, something like that, but no problem. We wanted to do it in the adventure way, to make the costs as low as possible, and to collect as much data as possible. Yeah.
So the goal of the trip, or the objective, was the data collection?
Yeah, data collection and sightseeing, of course.
And
no beaches and sunning near the sea. No, nothing like that.
Then why did you start in Hurghada?
Because it was the cheapest ticket.
Okay. Yeah. Because
flight ticket.
From Cairo, you have already very
of
nice
course,
sites.
yes. But there was a good price, so we fly to Hurghada. Yeah. Well, and why I decided to go there? I watched a lot of these videos on YouTube, a lot of documentaries. Of course, I watched a lot of videos from Ben, from Uncharted X, from Johanna, James, and also from the Scientists Against Myths or Sacred Geometry Decoded. And I always liked that all these people, it doesn't matter in which camp they are, that they can inspire other people to do their own research, to make their own measurements, so they can make their own opinions on something.
And conclusions, yeah.
So I like the inspiration, yeah, definitely. So I was inspired too, and I wanted to make my own opinions. One of my colleagues, one of the surveyors, said once that how can you believe that the pyramids were built in this precise way if you don't measure it by yourself? How can you believe just by reading it in a book? So
how can you believe in Flinders Petrie's measurements?
Yeah, of course. Yeah, I decided to go there for a 10-day trip and to collect some data, 150 gigabytes of data. Yeah, a lot of photos.
So what sites did you visit? Luxor?
I visited Luxor, Aswan, and Cairo, of course, Giza. Right? So it was
Saqqara?
Saqqara, of course, Saqqara, and yeah. I did a lot of experiments.
Okay.
I've taken a lot of footage.
On site?
No, I did one experiment in Aswan, in the quarry near the unfinished obelisk. And it was also published, peer-reviewed. I will speak about it, so we can jump.
You took the pounder stone?
Yeah, of course. I had to do it.
And the beer? I mean, the explanation is I heard that they had a lot of beers and pounding stones and time to make it happen.
Yeah. Yeah, it's definitely there. Everyone can try it, and the visitors, the tourists, are encouraged to do it. The pounders are lying around there.
Do you have this kind of explanation video about before entering the site? Like
no,
they didn't play the video?
No, I think they do it only for larger groups, maybe.
Okay.
And we were only two.
Ah, yeah, so, that makes sense. Yeah.
Yes. So, yeah. So that's it. That's the motivation. And I prepared maybe pretty long presentation, but we will see how long it will take.
Because it's very visual. So I encourage every listener to tune in on YouTube or on Spotify, and so they can watch. Because on Apple Podcasts it's only audio.
Yeah. That's the reason why I tried to add as much images and videos as possible to the presentation. And maybe I should start with introducing photogrammetry to the greater audience.
Good idea.
Because it's a relatively frequent term nowadays, but not everyone knows how it works. So I will say a few.
Start the lecture.
Yeah. Let's do it. Funny thing is that photogrammetry was connected with the documentation of cultural heritage from its beginnings. It was invented approximately in the 19th century, shortly after the invention of photography. And many engineers tried to use these photographic images to reconstruct the shape of the photographed objects, like really a geometric reconstruction. And one of the first was Albrecht Meidenbauer. Actually, it was an architect. It wasn't a surveyor. again, it's interdisciplinary technology. And also nowadays, the photogrammetry is very, very interdisciplinary. You can use it anywhere where you need some 3D information, 2D or 3D information. And Meidenbauer used photogrammetry for documentation of cultural heritage. His motivation was also very interesting. The image on the right, the building there, it's the Wetzlar Cathedral. And Meidenbauer almost fell down from the cathedral during documentation of the facade. And he decided that it will be safer to take these measurements on images, contactless, in a contactless manner. And he tried to propagate this method of measurement between surveyors. And after a few years, this method started to be used as a fully equal method for metric documentation of cultural heritage.
So it's equal. So it was equally
equal
accepted
to basic surveying methods. Yes. So it was used not only for mapping, but also for the documentation of these architectural objects. And Meidenbauer was also the founder of first photogrammetric archive in the world. They created this Königlich Preußische Messbildanstalt.
I bet there's one word for this in English.
It's possible, yes. It's an archive, yeah, archive for images.
So it's a royal image archive, basically?
Yes. And they systematically collected image data about cultural heritage over Europe. They created these images on glass plates in the older times. And they collected some 10,000 of images of these cultural heritage objects. And it was very, very helpful because for example, this one, it's the French cathedral in Berlin, and it was destroyed during the World War II. And they could reconstruct it based on these photographs. Yes. So the value of these photographs, these images, is very, very high. What is great about photogrammetry is that it allows us to collect information not only about the geometry, but also about the texture. So it is very efficient, especially in the documentation of cultural heritage, because you see the various changes of colors, the cracks inside of some parts of pillars or something like that. And the basic principles that they used before were that they only photographed the object from various positions. They used a method called plane table photogrammetry. And what you needed was only these images. To take these images, you had to know the distances between these images. And
so on the image, 1 point means one image, or the lines are one images?
The lines are the rays from a point that is on the object, and it is projected into the camera on the image plane. This is only the position of a camera. Okay. Here stands a camera.
But in every direction where you have a line, you take an image, basically. You take a shot. Or it's one image per camera.
It's one image per camera. Yeah. Okay. Yeah. And it's based on intersections. You just measure image coordinates on image plane in 2D, and thanks to the central projection, you can project the line, the ray in front of the camera, and you will do the same for the corresponding point from another camera, and the rays will intersect in the space somewhere, and there is the point that you are looking for. So it's very basic principle, and it was very, very effective. Of course, nowadays we don't do it manually, and we don't use analog photographs, and There is a lot of automation, but first I think I should explain a few terms because it is possible that I will use these terms during the presentation. so it will be better to explain them first. In photogrammetry, we need to deal with these basic orientations of images. First of all, we need to deal with the interior orientation of the camera. The interior orientation describes the parameters of the camera, what is inside of the camera. So there are parameters like focal length, so the distance between the projection center and the image plane. There are parameters like the size of the sensor where the image is created.
Distortion of the sensor, I suppose.
The more important ones are the distortions of the lens.
The lens.
Of course, we can count in that the shape of the pixel is not a squared one. It could be something else, but there are a lot of distortions caused by the lens that is set up to the camera. And if you look at a point that is somewhere in the real world and you project it through the projection center on the image plane, this trajectory is not directly linear. It can be somehow distorted thanks to the radial distortion or similar things. And we need to describe these parameters so we can talk about photogrammetry. You cannot use any kind of images for photogrammetry if you are not counting in the interior orientation parameters. So if we can mathematically describe all these parameters, we can use the camera and the images taken with it for photogrammetric reconstruction.
When we were learning or studying control systems, and also we used computer vision for orientation. So when the robot was, the task was to orient the robot in the 3D space based on 3D or 2D camera images, but we had two cameras, so we could have a 3D data point.
Stereo.
It's a stereo camera, and we had to work with the so-called camera matrix. I suppose all this information are in the camera matrix describing the actual camera. So we can have a relatively precise measurement based on the image, because we can calculate these values and the reality based on these values.
Like I said before, photogrammetry is everywhere.
Yes.
Well, so these parameters, these interior orientation parameters, are determined in a process called calibration, camera calibration. If we have a calibrated camera, we can take images around the object with sufficient overlap, and we can measure identical points on these images. Maybe this one, the point 1, is measured on this image. Right? So we have 2D image coordinates in pixels on this image plane, and for the same point on another image plane, we can measure other image coordinates. And thanks to these 2D measurements, if we have sufficient number of points, we can reconstruct the relative orientation between these two images, how these two images were placed in the space relatively to the object in the scene. So basically these points, these identical points, are called tie points because they are tying these images together. And we reconstruct this 3D scene. It is mostly not in the right scale. It is not in a specific reference coordinate system. You cannot use it for metric measurement. It's only in 3D. You can turn it on your screen, but it's it's not usable for any metric.
So the scale still has to be fixed.
Yeah. So you have to deal with exterior orientation somehow. You either use special equipment like RTK modules. Very good example is that some drones have these RTK modules implemented directly, and they can help you to get the GNSS and inertial measurement unit data, so you can get the
absolute position.
The absolute position. The absolute position in a reference coordinate system, maybe WGS84 reference coordinate system, GPS coordinates. And not only the position and the height, ellipsoidal height, but also the orientation of the camera, because there is usually an inertial measurement unit implemented in the system.
So it's not using the compass of the drone?
Not only. There are many sensors inside. So that's one way. You can georeference the whole scene directly using the coordinates of the projection centers of individual cameras. But the maybe easiest way and cheaper way, if you don't want to invest much money into professional RTK equipment, is to use GCPs, ground control points. So you can measure points directly on the object, and you can use these points directly for the transformation of this model into the reference coordinate system.
So it's the same when you do the photogrammetry of something which is on a turntable and you put a scale or a reference.
It's very similar.
Scale on the turntable. So in every frame you will have this reference size.
The only difference is that if you have only a scale bar near the object, the only thing you can define for the 3D model is the scale. But if you have more than 2 points and you know 3D coordinates of all these points, you can transform this object into a reference coordinate system. You can define the direction of z-axis, and you can translate and rotate the object correctly inside a reference coordinate system. It doesn't have to be national or some other kind of reference coordinate system. It can be local, but or oriented according z-axis. Of course, you need to have these coordinates measured with higher accuracy if you want to do it in a reliable way. So these points are usually measured using surveying equipment, using total stations and similar things. And this is not very cheap, of course.
What is a total station?
It depends. It can be from 5,000 to 50,000 euros.
What's that exactly?
What's that? A total station is it's something like an electronized theodolite. What's the theodolite? Theodolite is it's an equipment that allows you to measure angles and lengths. It's it will be shown on some of the images, and it's geodetic equipment. So these are the basics, and of course nowadays we don't measure these points on images manually, but I remember the times when we had to. It was very interesting to orient 200 images manually for an object.
That's what I wanted to ask. If they did this in the 19th century, how did they reconstruct, or what did they reconstruct exactly from the printed images? What did they measure?
They measured directly on the images, and then they transferred these measurements on a plain paper. on a table. That's also one of the reasons why it was called plane table photogrammetry. And they reconstructed the shape graphically. They don't had to they don't had to compute anything. Basically, you could reconstruct it only using a few measurements on images and transferring them to another paper.
And they also had a reference in the image or on the image?
They started with the position of the cameras, the camera network. They created a network from cameras. They drew the orientation axis of these cameras, and they added also a small image planes where they could transfer the X image coordinates from the images. I think it's not easy to explain it without a photograph, but maybe I will explain it in here. Okay, so you can transfer to a plane paper the position of these cameras, like from a top view. And then you just measure on the real images the X coordinates for the point. And on the paper, you will draw a line for the focal length in the direction of the axis of the camera, and a line that is perpendicular to the focal length. And you will transfer this X coordinate on the perpendicular line on the paper, and you just connect the projection center and the transferred X coordinate and extend the line on the paper in the space, like here. You could create, focal length here, image plane here, and draw the X coordinates there.
So basically, they could measure the columns or the heights, the angles, everything on the image.
Yeah, of course, but they usually reconstructed the objects in two ways. Separately the top view and separately the vertical views, the facade views. So the process was different.
So these were 2D side views or top views, or
yes, exactly. So let's continue to the automation of the process. Like I said before, nowadays we used computer vision. You use the term too. And that's great about photogrammetry because all these tie points between images that are used for the relative orientation of the images, for reconstruction of the scene, are measured fully automatically. These different types of algorithms, like structure from motion algorithm, which is using another algorithms, they are searching for features in the images, and they are comparing these features between the images. They are trying to find matches. And what is great about this?
It's similar to optical flow, basically, to determining the
similar but different. Same but
the
different.
direction. So, for example, on video, you can determine the direction of the pixels or where they are moving, basically between frames.
Yeah, but I think this is slightly a different part of computer vision. And what is great about these features automatically detected in the in the texture is that these tie points can be used not only for the relative orientation of images, but also for the calibration of the camera during the bundle adjustment process. So you can really use any kind of camera nowadays for photogrammetric reconstruction without knowing anything about camera calibration.
Can we define the calibration? What does it mean for the people who...
I said it before, but it's...
I mean, technically, when we're calibrating a camera, we are just defining those parameters, right?
Yes, exactly.
Which they are unknown, but could introduce some kind of distortion.
Yeah, we have to know these parameters so we can. Okay, the light went off. No problem. So we can mathematically reconstruct the rays, the trajectories of the projected points on the images, and we can call it photogrammetry after that. So it's an automated process, and usually you will get something like this after the structure from motion, because the structure from motion is used only for this rough reconstruction of the scene. This is the point cloud from tie points. It's not a detailed point cloud or a 3D model. And after this part of the process, so we usually measure some points of some points on these objects. We can place
nearby the wall or the object itself.
Yeah, measure tape or something like that. Just for defining the scale, we can even use these coded targets, which is very effective because it is possible to automatically detect these coded targets in the images.
Because of its shape, or its
shape.
It's like a barcode for the camera.
The position is determined by this circle in the middle, and it is measured with sub-pixel accuracy, which is definitely better than just measuring the points manually. Because if you measure it manually, you can get to accuracy of 0.5 or 1 pixel, something like that.
What does sub-pixel mean here?
Sub-pixel means 0.1, 0.05.
Is it
pixels.
Below the pixel size?
Yes, below the pixel size.
Because
yes.
What's the size of 1 pixel on these sensors?
It depends. It's a few micrometers. The size of the pixel inside of your mobile phone camera can be around 2 microns, maybe. But for better cameras, high quality cameras, full frame cameras, it can be around 5, 7 micrometers. And it is always better if the pixel is bigger, because more light will fall on the pixel, and there is higher image
more
quality.
Information.
Yeah. If 1 pixel is 2 microns and the sub-pixel accuracy of measurement of image coordinates is around 0.01 pixels, well, you have to divide the 2 microns resolution 100 times.
Yeah, okay. Yeah. Because you just said here that the sub-pixel resolution could be 0.1 millimeter.
I said millimeter. Sorry if I said millimeter. Pixel.
Oh, pixel. Okay, no.
Yeah. We are always starting with pixels.
So the 0.5 is also pixel.
Yeah.
Okay.
Definitely.
Yeah, that's
pixel. Yeah. So basically everything is measured at the beginning only in pixels. And that is also the reason why the final 3D model is, or the first 3D model is not in the right scale. Yeah. So it's everything is measured only in the pixels. And in the beginning, you don't know how far away are the cameras from each other. There is nothing defined regarding the scale. So you need something like these scale bars to define the scale. Of course, you can measure something directly on the object, and you use the dimensions of the object to define the scale. But there are various ways how to do this. And when the scene is reconstructed, you can use other algorithms like multi-view stereo algorithm to reconstruct the detailed shape of the surface. You can generate a point cloud or a mesh. So yeah, the outputs are different. Yeah, we will speak about it later.
Okay.
About this one, of course. So Yeah, let's make it faster because I think I'm talking too much about photogrammetry.
No, it's good. It's a technical
Okay.
show, so
Okay. Okay, maybe someone will find it interesting. So what can we use for photogrammetric measurement nowadays? Well, if you would like to do it in a professional way, you would use a professional total station. This is the total station.
okay.
Yeah.
Leica.
So like, it doesn't have to be Leica. But of course, these are one of the best. And this device allows you to measure lengths and angles, horizontal, vertical angles, and they compute directly the 3D coordinates of the measured points. Of course, this is mostly for the local measurements. If you want to georeference, to transform the model into some kind of national coordinate system, you have to measure the ground control points using global navigational satellite systems equipment. So mostly, yeah.
Is your phone also some kind of station?
My phone?
Yeah.
No, it is
because
not.
it looks like that you're carrying like a photogrammetrical workstation in your pocket.
Yeah.
Can you show it to the audience? It's crazy.
I can, of course.
It's like a brick.
I had to rename my hotspot to a brick. It's 800 grams, but I really like these rugged phones, not only because of the size of the battery, because if you will be lost somewhere,
maybe this camera will pick it up. Yeah, it's crazy.
It's really heavy. It's 800 grams, but it has a projector and big battery and many functions. So if you are planning
to get
projector, I
thought a laser pointer, but an actual projector.
No, there is an actual projector. It's one of a few models that has this function.
That's cool. It's good for camping.
There is also a separate fan for cooling down the system. So yeah. If you are planning to get lost somewhere in the wild, take this phone.
You can still watch Netflix.
Yeah.
Or ancient technology.
Yeah. Until something will eat you. Yeah.
Until the battery drains.
Yeah, but this will survive. They will find it. They will find your footage. It can be a nice documentary out of it. Well, okay, so
lot of equipments. Yeah,
I think we can definitely use this one for photogrammetry too, but I did not tested it yet, but I'm planning to do it.
I don't believe you.
I had no time to do it. These last weeks were really crazy. You can do anything. You can use anything for photogrammetry. Maybe not anything. What is quite funny about iPhones is that they are not very suitable for photogrammetry because they have this image stabilization implemented inside, and it is impossible to turn it off. I'm not sure if it is possible to do it for these new versions of iPhones.
No idea.
I would like to know because the quality of the images is very nice, but the image stabilization that is inside of these iPhones can complicate the process of the camera calibration, because you are moving the camera and it is adjusting the interior parameters just to make the images sharp enough. And so
it's basically physically moving the sensor.
Yeah, I'm not sure how it works.
I think
exactly.
There are multiple ways. Probably there is.
There are ways how to do it in post-processing way, software way. But
cropping out.
Yes. You can see it in.
No, they have also the mechanical stabilization, because you can hear it when you shake it. You can hear it.
It's clear then, and that's the problem. Yeah. So especially in low light conditions, it could be a problem because the corrections are more severe. Yeah. So I prefer to use something where you can turn it off, or something much simpler that does not have these features like image stabilization. Yeah, and if you want to,
what about gimbals?
Gimbals are definitely better. Yeah. Yeah, you can even use these vlogger cameras, even your DJI Osmo camera, I think. Yeah, so
it would be so nice if they would have the same lens, same two lens in a stereo camera, basically, and you could just do this right away. Yeah, you know the distance of the cameras, you know the matrices, and then you can just calculate the point.
Yeah, that's true.
Would be nice, but.
Yeah, but there still would be a problem because the distance between the cameras is the baseline, technically, is very short. And if you would like to define the scale for an architectural object using a baseline that is maybe 20 centimeters long or 10 centimeters long, that would produce a lot of errors because there is a big extrapolation of the scale. Well, so basically you can even use these small types of drones, even the DJI Neo, it's 135 grams, we tested it, and it produced very nice results, but only in very good light conditions. Yeah, direct sunlight, not low light conditions. And
well, in Egypt it's good enough.
No, yes, but they will not allow it.
Yeah. They want you to hire someone local for doing it.
Of course, and it's also a question of national security because you could fly with these small drones to some military bases and took photographs of something that is sensitive. So I totally understand it. And you always need to follow the regulations, the local regulations everywhere in the world. We have also very specific legislative questions here in Slovakia. But we already adjusted it to the regulations, digital age. Yeah. And we had to make it the same like for the rest of the European Union. So it took us longer, but yeah, it's better now. So that's basically about the equipment, and you always need a photogrammetric solution, photogrammetric software that will process these images, and there are so many different solutions. Some of them are commercially available, some of them are free, open source, like this Measurum, the Alice, I'm not sure now, it's Alice something, Measurum software, or the Reality Scan. It's also for free now. It's distributed under Epic Games account, so anyone can download it. The SFM software is also for free.
I've seen the DJI Terra. I think there's a software where you can basically map any kind of field. My friend used it for surveying rooftops for solar panel installments, and he can just basically draw a rectangle on the map where he wants to fly, and the drone will fly around that area, and it will basically map.
It's a DJI software, so it's logical that it is connected with flight planning, and
in crazy details.
Yeah, definitely. It's very effective, and many surveyors and other specialists are using these softwares for mapping, for creating digital twins of objects.
Does the accuracy of the reconstructed object is based on the software you're using? So are there better softwares and worse softwares, or
well, there are definitely differences. every user should have experience with a specific combination of software, camera, lenses, and of course he should know what is possible to achieve with this combination in specific conditions for specific types of surfaces, lighting conditions. Yeah, so there can be always differences, even if you use the same data, the same footage, and you process it in different software solution. You can get different results because
that's what I wanted to ask. Which one is the best?
Again, it depends. It depends because, for example, the Metashape software is very robust. From our experience, it can align anything. Yeah. Even under not very good camera network configuration, it can align the images, orient them, and produce usable results. However, the reality scan is much faster. In some parts of the process, it is 10 times faster than the other solutions.
There's a price for robustness?
Yeah, of course. And for the reality scan, it doesn't matter if you have 10 times more images. It needs higher density of images, but it's faster, so it is compensated somehow. And there are also many other aspects, other differences between the images, between the softwares, because the reality scan supports processing of laser scans and automated alignment of laser scans and photogrammetric data.
And why didn't we use that so far?
We did not use it.
Yeah.
Because we don't have a laser scanner.
No, I mean, obviously we worked together on the vases, and you were the one who were basically creating the 3D photogrammetrical data of the vases we have scanned. But I think we talked about this too. It would be nice to align the photogrammetrical reconstructions with the laser scans to have the same scale. Because for the photogrammetry data, we didn't have the scale.
It is not a problem to transform the photogrammetric model onto another laser scan using, I don't know, ICP or iterative closest point algorithms or something like that, just to change the scale and the orientation and the translation of the 3D model. But it is done. It can be done automatically, which is important if you have hundreds of laser scan stations through a huge site, archaeological site or a building. So
you meant LiDAR scanning.
LiDAR scanning, yeah. That's laser scanning for me. It's like the TLS, terrestrial laser scanning. Yeah, but I understand that these terms are different in different countries. Or
I thought you meant the laser scans we had.
No. Yeah. That one is for me like a triangulation scanner, because it is not measuring length, it is measuring image coordinates.
By reflection angle.
Yeah, it is projecting a pattern, in this case a laser pattern, on the surface, and the camera is reconstructing the shape of the surface based on the deformations of these laser patterns. So basically it's a triangulation scanner, and there are various types of these triangulation scanners, not only the laser ones, but even structured light scanners can be considered triangulation scanners, because there is also always a projector and a camera. Yeah. So it's a triangulation. Yeah, and yeah. So these are the different software solutions, and the last technical slide here is that if you want to achieve the highest possible accuracy using photogrammetry, you need to take into account many aspects. I mentioned it before. It is about the combination of the equipment that you are using, and not only the hardware, but also the software. You need to create proper camera network around the object. You need to use sufficient overlaps. The angles between the camera axes should be usable. And of course, you should take the images under proper lighting conditions, which can affect the appearance of the surface. This can be dangerous if the surface is somehow reflective, which is if you are dealing with polished granite, right?
Or if you have a completely textureless or very homogeneous texture.
Exactly. Well, white, plain surfaces are
nice, clean alabaster vases.
Yes. Very, very bad for photogrammetry. And that is also one of the reasons why the LiDAR scanning, the terrestrial laser scanning, is one of the most used methods and technologies used for scanning of interior places in buildings, because the walls are white. There is no texture. It's not very effective to use photogrammetry.
What about this new artificial intelligence enhanced, I forget the name, but what Luma AI does.
Nerve,
yeah.
Nerve, yeah.
I don't know what's the full term.
Mm-hmm. It's basically neural radiance fields.
Okay, yeah. It's training a network to reconstruct the...
Yeah, it can help, definitely help, and there are many publications about this.
That's an interesting question. How did you find that Ramesses head, which was reconstructed by Luma AI? Because I would think that it's kind of interpolating a lot of data points, and it's not the true data all the time when it's recorded. Would it be a reliable source, or was it reliable compared to other photogrammetrical reconstructions?
You will see it in the examples, so we can get there.
But do you think AI is or these AI-based methods are relevant? Are they good enough to compete with traditional softwares like Metashape?
We have to test it more.
Okay.
Definitely, we always need to compare it to something, to some kind of reference. Yeah. Always.
Okay, fair enough.
Yeah. Okay. So I think that it was enough talking about photogrammetry, and we can go to something more interesting to the viewers, maybe. So let's go to Egypt.
Problems of the obelisk revisited. Photogrammetric measurement of the speed of quarrying granite using dolerite pounders.
Yeah.
When was this published?
In 2023. Yeah, a year after I was in Egypt. Yeah, it was a lot of work, and I decided to start with this one because it was properly published and peer-reviewed. All the other examples are...
In what journal was this?
Digital Applications in Archaeology and Cultural Heritage. It's an Elsevier journal, so it's a high-quality journal. Yeah. So the other examples are more like citizen science examples. They were not published somewhere, so I decided to start with this one.
Why not?
With proper science.
Why didn't you publish the other ones? I think they would worse.
Definitely, it could be interesting, but I did not think it is that important to publish it.
Okay.
You will see. Regarding the obelisk.
So this is the unfinished obelisk in Aswan.
The unfinished obelisk, of course.
Just to give a little bit of background for the audience.
1,200 tons.
Oh. Yes.
Yes, it's huge, really huge.
A huge obelisk, which was basically left there.
Yeah.
Nobody knows the granite
why.
Quarry. Nobody knows why, and there are a lot of speculations regarding the scoop marks, because the granite around the obelisk looks like it was removed with some kind of ice cream spoon or something.
Yeah.
Scooped out in a very...
They are called scoop marks.
Yeah.
Because of the effect.
Weird pattern.
Yeah.
But I have been also there, and it was very, very fascinating. There was another obelisk, or maybe it was even a statue or something, not an obelisk, which they didn't finish, and you could go in to this it's a weird... you can go to the bottom of this, and you can take this pounder and try to I did try to just get a feeling, how could you speed up this pounder on the bottom of this? How many space do you have? How much space do you have for this operation? And I don't know. It's a little bit suspicious to me that this was the way how they did it. There are a lot of different explanations. I think the mainstream explanation is that they used fire setting. They heated up the granite with huge fire, and then they poured it with water. They stressed the rock with this technique, and then it was much easier to just heat the granite and remove these layers with a harder stone. The other explanation is that they basically chemically decomposed the granite, which made it easier to remove, which I don't really believe that was the case here. It works in small scale, but I'm not sure if that was the case. And there are other interesting ideas with vibrations and sonical tool movements, which they could just tune the tool to the resonance frequency of the stone, and then it was easier to cut in. I don't know, but that's definitely a very, very interesting place, and I would say artifact.
Yeah, that's true. And that was also the reason why I was there. I wanted to try out the quarrying technique, the official quarrying technique, because a lot was said about the speed of quarrying using just by pounding the dolerite on the granite. And the numbers of the quarried material were very different across many studies, and I heard that it is 30 to 50 cubic centimeters per hour only, or 100 cubic centimeters per hour, 200, 500 cubic centimeters per hour. The numbers differed significantly.
How did they calculate this, or what was the base of the study?
That's the thing. The number, the 30 to 50 cubic centimeters per hour, is more connected with the detailed work with creating of the hieroglyphs and these reliefs using flint, chisels, and other equipment. It was measured by I'm not sure now what is the name of the author. It was Stokes. I'm not sure now.
Dennis Stokes.
Yeah, I think yeah.
He did the experiments with
yeah.
copper drag saws and tube drills.
Yeah. And that's the main difference, that the process for these fine works it is much slower. Of course, you need to concentrate more. You need to pay attention. You don't want to be executed because you destroyed some kind of Pharaoh's cartouche. Yeah. So definitely the quarrying process using the dolerite pounder, if you are doing this rough work, is much faster. And I wanted to measure the speed of quarrying photogrammetrically, and this is used. These are these dolerite pounders, which were found there.
The dolerite pounders.
Yeah. which were found there. I think 1,400 pieces of them were found there around 2000.
So that's the actual evidence for the pounding theory.
That a lot of them were found there. So of course they must have been used somehow for something. Yeah, and what is interesting is that in the past many experiments were performed to determine how efficient this process is. The first of these experts that tried to do it was Engelbach with his famous study, The Problem of the Obelisks. So it's more than 100 years ago. But he was an archaeologist. He did not look very deep into the metric and accuracy of measuring some volume. Yeah, I'm a surveyor, so it's a professional deformation that if someone tells me a number, I want to know how precise, how accurate the number is. But it is completely logical that
should come with every measurement actually, which we take.
It should, yes, of course.
The certainty of the information. Yeah.
And of course, 100 years ago, there were many limitations how you could measure volume of quarried material. So
we still have, as we figured out recently, we still have huge limitations today with the laser scanners.
Yes, we have. Yes. Okay, we moved a few decimal places, but there are still some problems.
On the micron level, we are still struggling.
Yeah. So basically, Engelbach looked at the quarrying process and at the problem of the determination of the volume of the quarried material as at a depth problem. He tried to get in some depth on some kind of area. And the question is, what was the area he was working on? Because some authors are referring to 1 foot times 1 foot area. And he was able to get to 5 millimeters deep on this area. But what is very interesting, directly in his work, he's mentioning that he was working on one of the quarters of a 2-foot task. The 2-foot task was these neighboring scoop marks. Yes, okay, let's call it scoop marks. Because one of them is 1 feet wide. Yeah, so a 2-foot task. This was the working area for the craftsmen, ancient craftsmen, and the 1/4 of it is this, and you can see that it is not a square. So I suspect that he wasn't working on a 1 foot times 1 foot area. He was working on a 1 foot times half trench wide area. And
there was no image drawing anything on the...
It was, but the specific location where he worked was not there. I think maybe I missed it. Correct me if I'm wrong. If someone knows,
do we have an image from this?
Let us know. But
from this publication,
not in this presentation, but
we can insert this later.
Yeah. Okay. So what is clear is that that Engelbach determined that the width of the trench is 2 feet and 6 inches, which is approximately 0.75 meters, approximately, or 76.
There's the width of this trench, or this.
It's the width, the width of the trench. But of course, it differs. It changes. Somewhere it is 0.6, somewhere it is 0.9. So we don't know where he was working, and never mind. If he was able to get to 5 millimeters deep within 1 hour, for this area, this corresponds to 572 cubic centimeters per hour.
That's a little bit crazy.
You think?
Yes. No?
It's a very nice number.
It's an ambitious number.
Yeah, ambitious. Well,
I was also there. I also tried the poundings, but
well, I
I'm not
measured
a
it.
skilled craftsman.
It's not that crazy.
Okay.
This estimate is not that crazy. Other scientists in other experiments achieved a similar number, not that high, around 30 to 300 to 400 cubic centimeters, but it was possible. I think that the difference between this number and most recent experiments is caused by the method of measurement of these 5 millimeters, because I don't think that Engelbach was able to measure accurately the depth, the average depth over this whole area. How would he do it? I'm really not sure how.
I have an idea how it would be possible, but probably it was not the case. So if you have these, maybe we can insert some kind of visuals of this.
Okay.
If you have a set of like these, how is it called in English?
Sticks.
Like these I don't know, these sticks. You have this in an arrangement where you can basically pull your sticks until it reaches the regional depth.
Okay.
And based on all of these little sticks, you can basically just sum up the depth and you can get the volume.
Yeah, that could work.
It would require some kind of nicely arranged and fixed like a frame where you can adjust the height of these sticks, and I don't know how it's called. What's the term for this? But I'm sure it would be possible. Yeah, it would be not that accurate, but more accurate than
But we have no idea how he did it, because he takes no notice about it. There is no information about the method of measurement, of the depth, only an estimate.
That was the case when we did measure the Lahun granite box, which Petrie measured in the Victorian era. There is no account on what did they use for, or what he did use for measuring it. We can kind of estimate what method he used for measuring the flatness of different features of this nice granite box, but we don't know. But the nice thing was that we could verify that his measurements were kind of correct. The 0.1 millimeter average flatness, or even less. I think it was 0.004 of an inch or something like that. It was a very nice experiment, but still the problem is that we don't know how it was measured exactly and what was the error of the measurement, or
Well, what was very interesting in the Engelbach's work was that he achieved this depth, and he estimated that the ancient Egyptians could achieve even more, almost twice.
With more beer, or how?
I don't know. They were more skilled, of course. If you are doing this for the living, yes. You can do it better.
But how would he define the multiplication rate of the skill itself?
Yeah.
I mean, it's like, okay.
I suspect I know why he used these numbers, but we'll get to it.
Okay.
So this was one of the first studies. Röder in 65 calculated, doing his own experiment, that he was able to quarry 120 to 180 cubic centimeters per hour. But again, he extrapolated, and he suggested that the ancient artisans could achieve 4 times higher speed of quarrying again.
But what was the reasoning? Why?
I don't know. No idea.
Okay.
Again.
That's weird.
It wasn't stated there again. And Lehner in 1997.
I was born that.
Oh, yes. You were born in the time of experiments. Yeah. Where Lehner, after 5 hours of processing on this, again, 1 foot times 1 foot area, reached 2 centimeters depth. And if you calculate it to the volume, it would be 360 cubic centimeters per hour. This is very reasonable number, okay, I have to say. And what all these studies have in common is that, there is no information about the weight of the pounder. You have no idea what was used.
You would think that as an engineer that it's a quite crucial part of the study. It's
of
quite
course,
important.
Of course, it should be more effective if you use a pounder with bigger weight. Yeah, and it was actually proved by other team. I will get to it.
Just try to use a 1 kilogram of sledgehammer.
Yeah. Another very important information is that there is no information about the hits per minute. Yeah, the frequency. We don't know what was the accuracy of these values, and we have no idea about the method of measurement of the volume. So this was something that motivated me to perform my own experiment. And I was also very interested in one more experiment that was done by Kruglyakov in 2019. They even tested 2 different pounders of different weight. They reached these numbers, very, very similar to the Lehner's. Yeah. They even recorded the frequency of pounding.
Why is it varying that much?
It is varying because they, I think they switched the persons that were quarrying during the hour. Mm-hmm. Everyone wanted to try it. Okay. Actually, there is a video on this link. It's on the Science Against Myths YouTube channel. And it was very, very interesting experiment because they took 50 kilogram granite boulder and they weighted it using industrial weighing scales or weighing scales. And they weighted it before and after quarrying, always.
Okay.
And they have done this not only for the granite piece, they have done it also for the dolerite pounder.
Yeah.
So
how many material you lose during
it's totally logical that you are turning into dust not only the granite but also the dolerite, and it was very important to see and very interesting that it is truly effective, that the granite is wearing off faster than the dolerite.
Mm-hmm.
Okay, so maybe what could be a shortcoming of this study is that they performed it, they used the local materials in Russia, not the Egyptian ones.
Yeah.
So maybe there could be small differences, but not big enough, I think. And you cannot take industrial weighing scales into ancient archaeology sites. It's not very practical. So I decided to perform photogrammetric measurement. This is the location of the boulders that you can use for practicing if you need to exercise.
Is it after or before is it that obelisk we are talking about?
Yeah, that's the unfinished obelisk, and the boulders are behind it. Yeah, so the top of the obelisk is in this way. Yeah. So we will come through the archaeological
because there are
site
several
from this
obelisks.
side. Yeah. This is the unfinished one. Yeah, the big one.
There's the crack in the middle. Yeah.
Yes, that's it. Well, so we performed the experiment only with one boulder, and We placed also a GoPro camera in front of it, so we could
Nice head.
record the. Oh, thank you. It was hot there, 45 degrees Celsius. But great weather for exercising, really.
But you are like me. I also, when I was there, I was in long pants and long sleeves, long shirts. It's effective.
You need to cover the body because you would be burned all over. Yeah. So there are basically two main or three main techniques how you can quarry the granite. Either you can hold the dolerite pounder in your hands for the whole time and just smash it, or because your wrists will start to hurt. So sometimes you can change the technique. You can try to throw it, but it tends to jump off the surface, and it is not very easy to catch it again. So sometimes it can be dangerous.
It can hit your toes.
Or the camera.
Experience. Are you talking by experience? So you hit the camera?
It almost happened, yeah. So sorry, Martin. It was the camera on my friend. Yeah. So these are maybe the two basic techniques. The problem of the second one is that the frequency of the hits is lower. Yeah. And one more technique would be to move the pounder across the grinded, but it's effective only if the dolerite is rough enough. Because after some time it will start to be not polished, but it will be more smooth, and the process is not that effective. Yeah. So I think the first version with the heating is more effective. But
did you walk down to the other obelisk where you could go into the scoops?
Yeah. I was there also, but I did not perform the quarrying there.
The scoop was almost vertical, or sorry, it was almost horizontal.
Almost horizontal.
And I was wondering. You can squat before that scoop, but you have if that trench is full of men, you don't have enough space to give enough power to your pounder to be effective.
I think all of this should be reconstructed. Experiments should be performed, not in such an individual way, but using tens of men, shoulder to shoulder, working in a trench and measure the effectiveness, even with the pauses for removing the dust, the removed material.
The blow pause.
The blow pause. Yeah, because it is causing a kind of a cushion effect.
Yeah, exactly. It's covering and decreasing the power of the pounding.
So you need to remove the material, the debris. It has to go somewhere. And if you are 3 meters deep in a trench, maybe you have a basket and you can fill it with the debris, and you will just hand it over to someone else.
Also, the regular.
You need space for it.
Yeah, for sure. And
regularly. Yeah.
But the regularity of these scoops, and that they were not straight, they had an offset in a different angle, or in a certain angle. It was, I don't know, for me it was very hard to imagine that 100 people were just pounding this way to have this slope in the scoop. I don't know. It's weird, but let's continue.
It would be very interesting to try this and measure the actual effectiveness in this huge number of people. Yeah. So what I did was that I took images of the granite boulder, granite block, before and after the quarrying process. I was quarrying only for 15 minutes. I like my wrists. I'm not sure now who told it, but who said it, but you don't feel your hands after the process, and if you would work on a computer after the quarrying, you could destroy the keyboard. So, and yes, it's true. It's really a hard work. Yeah, I use a mirrorless camera, Sony Alpha 7R free camera for taking these images. Altogether, there were some 113 images, and I oriented all these images in one image block, and then just turned some of the images off and created two 3D models. Two 3D models, the one before and one after, and computed the differences between them. Yeah, and so I could calculate the volume. Also, inspired by the experiment of Kruglyakov, I took images of the dolerite pounder. I had no weighing scales with me, and I wanted to know what was the weight of the pounder, so I created a 3D model of it. And since we know the density of the Egyptian dolerite, we could calculate that the pounder weight was 3.47 kilograms, so pretty easy. And here is the difference model with the deviations between the before and after quarrying.
What happened there on this lower part?
Yeah, there was some debris inside of it, and it was blown away after.
Okay, I see.
Yeah, I did not see it before, and did not notice it. So yeah, it's there, but the quarried area is in the rectangle. Yeah, and here you can see that after 15 minutes of quarrying, I could reach the depth of 8 millimeters on this small area.
So it's millimeter, the scale is in millimeters.
Yeah, it is in millimeters, yeah. And I was able to quarry some 54, I think, cubic centimeters. It will be somewhere in the tables. One more additional thing, what was interesting, using the GoPro camera, we could calculate the speed of the pounder on the impact, and we could calculate the energy on the impact. So photogrammetry is very versatile. You can use it for anything, even for dynamic events, analysis of dynamic events. There exists also videogrammetry or 4D photogrammetry. So you can 3D model dynamic moving objects in 3D and analyze them. So basically, we determined the size of the pixel on the GoPro camera. The GSD, the ground sampling distance, was 0.42 millimeters, and thanks to the changes between neighboring frames, we could calculate the trajectory. There are 269 pixels between the two positions of the pounder, and thanks to the known size of the pixel, we could calculate the real distance that the pounder traveled in space. And since we know the weight of the pounder, we could calculate the energy. So yes, that's pretty everything. And here is the result. So for the 15 minutes of quarrying, it was the 54 cubic centimeters. And if we multiply it by 4, we can get the number for 1 hour. So I reached 216 cubic centimeters per hour. And the pounder was the weight of the pounder was somewhere between the pounders that were used by Kruglyakov and his team. The frequency of the hits was smaller. Of course, they performed the experiment in maybe 20-25 degrees Celsius, not higher, in garage, and they seated near the pounder, and I had to stood there in 45 degrees sweating. So, and of course, I tried various types of the pounding techniques with the throwing, and it was slower. So, yeah, I think it is totally logical that I didn't achieve that high number as they did. But, yeah.
But it's still very close to the 222.
Yeah. So, I think it is definitely more effective than the 30 or 50 cubic centimeters per hour that were mentioned many times. We can definitely speak about hundreds of cubic centimeters per hour, but maybe not about
900.
600, 700, 900. Yeah. So not only using this kind of methodology of quarrying. Yeah. I think that something else must have been involved.
Did anyone consider the fire setting, that the rock was stressed? In these previous studies, did they consider?
I don't think so.
Because that's what they say, that the rock was stressed and it was easier to remove.
Well, of course, they maybe counted this in their extrapolated numbers for the ancient Egyptians. Yeah,
but
it is possible. But again, we don't know.
Extrapolating is not very.
Yeah, of course, and saying that something was 2 or 4 times better than your achievement, than your own achievement, it's strange. But okay, I think it was possible to achieve 300, 400, maybe even 500 with a lot of practice cubic centimeters per hour just by regular pounding. It depends on the size of the pounder, of course, and if you are strong enough, you can get high enough frequency with a heavy pounder. Okay, but I think definitely something else must have been involved too, because we know that the pounders were somehow involved.
They were used. They were made for something.
Yes, and I think they were used for the process, because the school marks, and especially the places on the bottom of the trench, the 4 quarters are like working areas for this process.
Okay.
And the worker just had to change the side, and he moved on another part.
Did you calculate how much time would they need to remove the entire, or to basically carve out the obelisk?
Yeah, I did. I'm not sure if it is in this presentation. I think there is only a calculation for the Hatshepsut.
Okay.
Yeah, but for comparison, I think this is enough. The Hatshepsut, the obelisk of Queen Hatshepsut in Karnak.
I think this unfinished was also connected to Hatshepsut, which they left.
Yeah. Well, this one was definitely finished, and thanks to the hieroglyphs that are thanks to the writings that are on the obelisk, we know that it was quarried in 7 months. It is smaller, okay, but it is still huge.
How much smaller?
It's around 29 meters. I'm not sure now.
I mean, in weight, is it much lighter?
Yes, it is. But I don't remember the number now. But the Engelbach's calculations, because he was commenting on the quarrying of this specific obelisk, and he was comparing his numbers with this value, with the 7 months. And I think that is also the reason why he chose the 80 millimeters for the ancient artisans.
Oh,
yeah, because if he used this value, this 8 millimeters, and the dimensions of the trench for the Hatshepsut's obelisk, this smaller one, and he calculated that it would take 4.4 months, working 12 hours a day, to get to the bottom of the trench, and another 4.4 months for undercutting. Altogether 8 months, which is very similar to the 7 months that are on the obelisk. So I think that could be the reason for this extrapolation, but I don't know. Yeah. Never mind. If we use our numbers, the real achieved volume of material removed, we will get different numbers. So if he would use only his 5 millimeters, he would end up on 14 months for the Hatshepsut's obelisk, for the smaller one. If he used the 8 millimeter estimate, he would get to 8.7, 8.8. There is only an error in
rounding.
Sorry, I need some Guinness. Sorry. It's 0.0, but yeah.
Refreshing. Welcome back to the Ancient Technology Podcast. If you enjoy the show and want to help me creating high-quality episodes, consider supporting me on Patreon or becoming a YouTube member. You can find those links in the description. Your support gives you early access, a say in the podcast direction, and exclusive perks like post-show bonus content. Most importantly, it helps me travel to meet guests in person, which is a key to producing the most engaging and in-depth episodes. Thank you for considering, and now let's get back to the show.
So, with our numbers, even with the Kruglyakov numbers, with the heavier pounder, we would end up on 25 months. And for the unfinished obelisk, which is much bigger, it would be even more. Definitely a few years of quarrying, 12 hours a day. Yeah, so I think that something else must have been used with the pounders, either the fire, yeah, of course, or anything else. It could be effective, but it should be tested again. And the quarry material, the removed material should be measured. So we can make the comparisons. Yeah. Okay, let's jump to some final remarks to this study, so we can talk about other topics. I said that the Kruglakov's experiment was very interesting, especially because of the measurement of the effectivity of pounding dolerite on granite. They reached these numbers. They were able to remove 222 cubic centimeters of granite within an hour, and only 83 centimeters of dolerite were changed into dust.
Cubic centimeters.
Yeah, cubic centimeters, yeah. When they used heavier pounder, again, yeah, the quarrying was more effective. Maybe with an even heavier pounder, it would be even more effective. It should be tested. I
think that the two numbers are very close to each other. I mean, the 83 and the 73 is quite close, so it can be the difference due to the irregularity of the rocks, different material, different type of...
Yes, and it could be somehow related to the technique of hitting the surface.
Yeah, maybe.
It is possible. Yeah. Who knows? I think there is one more interesting aspect regarding this process of quarrying. The trench around the obelisk is, the volume of the whole trench is around 400 cubic meters. Yeah.
You mean the whole trench?
Yeah. The whole trench around the obelisk.
On the bottom, or you also counted the walls because it's a deep
They
trench?
had to remove 400 cubic meters of granite out of the bed, from the
very
bedrock.
top,
Yeah, from the bedrock.
The bottom, yeah.
That's a minimum. Yeah, I'm not counting in that they had to somehow level it, because we don't know what was the shape of the bedrock when they decided that, okay, let's go to quarry an obelisk here.
Yeah,
we don't know what changes of terrain they had to do. So only for the trench, it's 400 cubic meters, and if we use these estimates by Kruglyakov, we should take into account that more than 100 cubic meters of dolerite would be changed into dust. Yeah, and you of course cannot use the pounder until the moment that it will disappear in your hands. Yeah. So the question is, when they decided to throw this away, that it was unusable. That's the question.
That was the state where it was found in.
Yeah.
It was already.
That's also one of the theories
away,
that what we found there was only the debris, only the pounders that were left over, that were unusable. So if we calculate these 115 cubic meters into number of pounders with average diameter of 14 centimeters, it would be 85,000 pounders. But you need to take into account that they were thrown away after removing this amount of dorite, and maybe they were thrown away when they lost half of their weight. Maybe, I think that's a good estimate. That would mean they needed 170,000 pounders for the whole process.
Do we have that much dolerite in Egypt?
I don't know. This is not a question for a surveyor, but I think this is very interesting to take into account. And of course, we found only 1,400 pieces of these pounders. Maybe they just collected it, the remaining ones, the 80,000 pounders, and they moved them to other locations where they were again used for
smaller tasks.
Yes. So who knows? What we know for sure about Egyptians is that they were very effective and very inventive. Yeah. So, okay, that's what.
So the conclusion of this paper was that basically the data we have seen so far from these studies were not that accurate, and they were working, or it's the rate of working with these pounders are much lower than we thought so far.
Yeah, I think this is not something that is closed. It's not we don't have a clear conclusion about this. And more experiments should be performed, definitely.
How much time do you need to carve out the full 1,200 tons of obelisk? How many years do you need for that? And if they had enough time to do it?
Very good question.
During the reign of the ruling pharaoh. I think it was Hatshepsut, but I'm not sure.
Yeah.
Or how is it related to the claimed time frame of the process, of the manufacturing process of that object? Did they need much more? And how much more?
That's the question, because we have to calculate not only with the time needed for the quarrying process, but also for the testing shafts.
Yeah,
because there are some shafts and they are much deeper than the trench.
Deep. They are crazy deep.
Yeah. So
and very narrow.
Almost twice that deep, like the trench itself, and you would need twice the time to get to that deep.
So they needed
depth.
They needed to test the quality of the bedrock or the granite, so it's worth the time and effort to carve it out.
Yes, definitely. Okay, and of course you need to transport it somewhere. You need time for the transportation, and you need to finish it. And especially the finishing of it took a lot more time to polish the surface, to create all these nice writings and reliefs, these hieroglyphs. So it's it's astonishing what they were able to achieve. Truly, yeah. It amazes me. Yeah. Okay.
Was it easy to publish this paper?
Yeah, there was no problem to publish it. Everything was peer-reviewed. The data was correct. Yeah.
Nice.
No problem. Okay. Let's go to another topic. Like I said before, I like citizen science. And,
nice one.
What I love about photogrammetry is that it really allows people to get their own data, even with a mobile phone. I love the possibilities nowadays that the technology is available to anyone. Yeah, everyone can get a smartphone, and you can make measurements in a safe, contactless manner, and you can draw conclusions out of these measurements only using a mobile phone. So again, I think everyone knows this object is the unfinished sarcophagus of Hordjedef, which is located in the Cairo Museum. And it is a great example of the process of creating these sarcophaguses. I think that if the ancient artisans did their mistake during the sewing process, we wouldn't know how they created the lid for the sarcophagus, that it was a part of the original box or original block of stone, and that it was very important for them that it is from the same stone. It's not only about the shape. If it was important, they would finish it, and they would place some other lid from another block of stone on the sarcophagus, and there would be no problem. But they abrupted the work, and it was found unfinished and used for Hordjedef. And a lot was said about this sarcophagus because there is this very interesting saw mark. And there were these ideas that it is an overcut, and that
looks like a circular cut.
Yes,
at some point.
Yes, and I decided to create a partial photogrammetric reconstruction only using mobile phone images.
Wow.
Yeah. So the blue dots were the positions of the camera, and here you can see the only partial reconstruction.
You see inside this cut?
No, unfortunately,
really.
no. It was very, very thin. Yeah, and actually, we can see that there was a prescribed line, original line, which they in which they wanted to saw, but they deviated somehow from the original direction. It's here. Yeah, you can see it. And it looks like they realized their mistake after 1 meter of sawing, and then they tried to return back to the original line. Okay? You can see it, that there is an angle change of.
So the sewing was not performed from top to down as it is laying now. It was basically sewed from. So if you look at the image, where was the actual copper saw they used? They were sewing it vertically, or they were sewing it from bottom to top?
I think it wasn't cut in the position in which it is laying there now, because it is only for exposition reasons. I think it was standing on this side.
And they were cutting from top to down.
Yes, from top to down, because it is easier to cut through shorter piece of granite.
Yes.
Yeah, that's one thing. Another thing is that if they used these arsenic copper saws with abrasive materials and water, you need to you need the abrasive material to stay inside of the cut. Yeah. So it cannot be in this position and move the saw vertically. You have to move the saw horizontally and to have some abrasive and water inside of the cut. Yeah. So that's the basic idea. And the reason why this sarcophagus is so controversial for some people is that there is this specific saw mark which looks slightly bent, like it was created with a circular saw, like this one. And it must have been saw with radius of 1 meter. It's crazy for me. Yeah. Well, there are several reasons why I don't think a circular saw was used to cut this lid off. One thing is that such a saw wasn't ever found in Egypt. Okay, it could be logical that it was recycled into something else because it is metal. So it's logical that we have not found
circular saws.
Yeah. Okay, they could have been somehow reworked, but I don't think there are any depictions of using circular saws. I don't
haven't
think
seen
so.
Yet, no.
Okay. One more thing, the cutting would have to be done from 2 sides, because this cut in the upper part is also here down. It's only hardly accessible. And one more thing why I think the circular saw wasn't used is that the cut is not ending here. It is ending here somewhere.
It's just a matter of a bigger radius and a different position of the circle.
Okay.
Like shift a little bit.
Okay, but then we would talk about a saw that is 5 or 7 meters in diameter, something totally huge. And the question is, what would be the thickness of the saw? Yeah. Well, never mind. I decided to analyze the inside of the cut, the bottom. Because if the saw was circular, Also, the bottom of it should be circular. It should be visible there. If they ended here after breaking off the lid. So I took 2 images that were close to each other, and it was possible to see inside of the cut. This is a detail. You can see the texture on the bottom of the cut here, and I identified identical features, identical points on these 2 images. The baseline between the images was long enough, so the intersection was totally sufficient for reliable determination of 3D coordinates of these points in space. And you can clearly see that the inside points of the cut and the starting and the ending point of the cut are on one line. So the inside of the cut is linear. It's not circular. Also, another reason why I think it is a linear or straight saw was used for the cutting is that there are many saw marks that are linear. Actually, this is also linear, but there are some textural elements which can look like something that is bent, but it is actually straight. Hello, Ellen, from Sacred Geometry Decoded. Thanks for the image. You can see parallel striations, but you can see them only under proper light. So they definitely look straight. And again, it is an evidence of using these abrasive materials during sewing. Yeah. And one more interesting thing, here is another saw mark. And again, it is linear. It was also visible in the historical images. And I think this is also the evidence that the original direction of the sewing process was according to this saw mark. So the saw was oriented in this direction. Yeah, but of course everything was turned up on this, like this way.
We have this, yes, we have this weird cut or overcut or whatever we call it, because they tilted the saw during the cutting process.
Let's look at the reconstruction of the process. What I think happened.
Okay, yeah.
I think they started this way. They reached the 1 meter from the beginning, and they noticed that they went off from the original direction. So here they realized that it would be nice to correct their mistake. So they changed the direction of sewing into this 45 degrees version. And of course, changing the sides.
How did they leave the abrasive in?
Again?
How did they leave the abrasive in? This was one argument before, that the abrasive would fall out. It wouldn't stay in the groove.
Well, that's the question. Maybe they tilted somehow the whole block 45 degrees to a side. Maybe. I'm not sure how much material,
or
how
they
much...
used fixed abrasives, as we suspected so far, and also Petri. And it was not just sand and water, but it was some kind of fixed jewel tips.
Who knows? Yeah.
Okay.
I don't know. Well, so they changed the direction, and when they reached this depth, something changed. Something happened, and the lid broke. Yeah. and they abandoned it.
Do you have a 3D non-textured surface reconstruction of that cut?
The inside of the cut?
Yeah.
It was impossible.
This straight part.
This straight part?
Yeah.
Well.
No, I mean the part which is curved, looks curved, but it's straight. Do you have a closer 3D?
It should be. Wasn't it here somewhere? No, it wasn't here.
No, it was just a straight one.
Okay. Maybe I will open the photoscan project, Metashape project. Okay. Either way, one more interesting thing, if you fit an ideal plane through the original direction of the sawing and compute deviations from it, you can see that the saw must have been somehow bent inside of the cut. Also, 3 centimeters bent from the original line,
which is not really possible with the circular.
Yeah, and
it's possible, but it's less likely.
Yeah, and it is also very interesting that in the lower parts the deviations were smaller. The problem was here, especially in these parts, and I also suspected that maybe the tension that was inside, thanks to the bent saw, could be somehow related with breaking the lid because of lever effect. But okay, the granite lid was some 15 or 20 centimeters thick, so I don't think it was possible for a human to break it, even with a lever. I think that if something happened, maybe it fell down on the side of the lid during manipulation, maybe even during the rotation of it, so the abrasive will not flow out. Maybe, I don't know. This came to my mind only right now. So it was heavy enough to break it. It's 9 tons, I think.
I don't know. No
approximately.
idea how heavy is it?
It was approximately 9 tons, I think. Yeah. So, it's very interesting example of how a regular device that every one of us is wearing in their pockets can be used to analyze an ancient object. Yeah.
I also discovered that if you remove the texture, the geometry will be completely different. I mean, not different, but you will see those details that you would not see because of the camouflage effect of this texture.
And I think that is it is a very good example, especially for these saw marks and
Karnak?
overcuts. Yes, it's in Karnak, because the texture can really change the perspective of what you are seeing it.
Yeah, I love those drill holes and cuts here. I think that there is a huge cut over there. I think I did also some photogrammetry here.
Oh, it's a very nice object for photogrammetry. Yeah. Actually, I had a big problem to find it. First, I was going around for 1 or 2 hours.
It's a huge place. It's a huge place.
It is very interesting that it is the 6th pylon here, if someone would like to find it. So this is the main entrance to the Karnak temple, and you are going through this alley, and somewhere here, these are these pylons, and they are very interesting because of these like saw marks, vertical and even horizontal saw marks. Here are a few moving images.
Yeah. Looks like someone went there with an angle grinder or something.
Yes. Looks like that.
Took a line.
Well, and the one that I was very interested in was this. It looks almost like an overcut almost. And definitely it is mentioned as an overcut in many videos online. So I definitely wanted to look at it. And yeah, if you use photogrammetry, you can remove the texture, like you said. Yeah. So if you remove the texture and even add some depth information and colorization based on depth, you will see that it is not an overcut, but it is an overlapping glyph or relief, a depiction that interferes somehow with this original line. Yeah. The question is, what was there first? The frame, the straight line, the frame, or the depiction, the relief? But that is not a question for a surveyor. I have really no idea. I can only say that it is not an overcut. So photogrammetry helped, definitely.
Nice.
Yeah.
But the cut itself is still, I mean, how and what's that? Why there is a cut next to this glyph? If the glyph's supposed to be the information on the wall, why do you have a huge cut?
Maybe it is connected with the time when it was added there. Maybe the glyphs were added later.
Or it was
or
reused
opposite,
or
in the opposite way. Maybe it was reused by someone. Yeah. If you are looking here, this looks almost like someone tried to remove the granite. Because especially thanks to these cuts, you could remove the material maybe better, more efficient.
Yeah,
I don't know.
My idea was that maybe they wanted to remove this corner or make a corner in this wall.
Yeah. Maybe. Who knows? It would be great to speak with someone from other profession. Yeah, with historians, with archaeologists who have more information about these pylons. Yeah,
Just shoot me an email.
Yeah, definitely. I think that all of these objects are or represent interdisciplinary problems. So every profession has something to say to these objects. And I think that we can get to some reasonable, reliable results only if we stay in the areas of our expertise and let other experts do their own work. So I totally respect all the archaeologists, historians, mineralogists, geologists, chemists, everyone. Yeah. So, yeah. Let's think about them together. Yeah. Okay, this is an example from the opposite side, and you can even see that it is not a straight line.
Yeah.
And again, it was proved, I think, by these scientists against myths. They had performed a few experiments. How it is possible to create these very thin lines using just these abrasives. And what is very interesting, they are very sharp. Okay? It's this one.
Mm-hmm.
Very, very sharp. Again, I could not resist to create a photogrammetry reconstruction. So they are approximately 7 millimeters deep, 2 millimeters wide at the top, and at the bottom only 0.3 millimeters. So very, very, very sharp. And as I understood it, you don't even have to own these very sharp copper tools. They don't have to be sharp at the beginning.
It's making themselves sharp, by the grinding. Yeah.
Exactly, yes. So if you go deeper, it will be sharper. So, yeah. Okay.
That's what she said.
Okay, let's go to other examples. How much time do we have? Half an hour. Okay. I hope we can do it. So let's leave the saw marks, but stay in Karnak. Karnak is very interesting for these objects. There is this huge open air part museum where are many of these fragments of destroyed buildings, pillars, statues, and somewhere between them lies a huge fragment of a hand, one of the Ramesses II statues, a truly colossal statue, which, by the way, is reconstructed now. I think I'm not sure how far are they with the process, but they are trying to put all the pieces together and reconstruct the statue.
Okay.
Yeah.
Are you working for them?
No. I just saw it somewhere that they are working on it. Well, unfortunately, when I was there, I couldn't find it. But luckily, Ben was there from Uncharted, and
I've also seen it with
yeah.
Ben. I can also send you the Luma AI reconstruction if you need.
You have it?
Yeah.
Excellent. Great. Please.
Okay, yeah, deal.
Okay, because the LiDAR scan provided by Ben, it was very nice because it was in scale. That's great about these iPhones and LiDAR that is in the iPhones, because basically from photogrammetric measurement, just from images, you cannot get the scale.
Yeah.
You need to measure something.
You need the reference.
Metric, yeah, you need the reference.
But with the LiDAR, you have the speed.
It's not that accurate, it's not that precise. It's around 1 centimeter on 1 meter, the relative accuracy, but it can help you. And I used it to estimate how big was the original statue.
Nice. Because this is just the
fragment. Yeah.
The fist.
Yeah. Okay. But to do it, I needed some other Ramesses II statue. There are a lot of standing statues of Ramesses II all over Egypt.
No, they have one in the Grand Egyptian.
Yeah. There were actually 2 of them in that area, and one of them is in Memphis.
I think they moved the other one from Memphis to the Grand Egyptian, and it's full standing with the legs. Is it the same size? I think the one in Karnak had much bigger fist.
Yes, it was much bigger, and that was also the reason why I wanted to estimate the size of the one.
Makes sense.
Yeah, but the 2 ones, the one in Memphis and the one in the Grand Egyptian Museum, are of the same size.
I think they are same. Yeah.
Well, unfortunately, not a complete statue was available during my visit. So again, I used only my phone to take some images to get to the whole shape. The crown was missing, hand was missing, legs were missing. So
I can give you photographs of the Grand Egyptian one. Which is in the Grand Egyptian Museum, so you can compare the scale.
Okay. We can do it.
Maybe.
Well, definitely this was a bit like a Frankenstein work. Putting all the pieces together.
Looks like.
to create something complete. But
40 cubic meters.
40 cubic meters only for the statue without the pedestal. I have done this with one of my students, and if you count in the density of limestone, you will get to 106 tons only for the basic statue that lies in Memphis. This is the smaller one. With the pedestal, add 30 tons more to it. So
I think the biggest one was in the Ramesses with 1,000 tons.
Yeah, and the Colossi of Memnon are also very, very huge. Yeah.
Have you seen the Ramesses one? I think it's Only this.
The Colossus that were
not the
on the
Colossus
side.
of Memnon. No.
I know. But there is also this Colossus in Ramesseum,
Which
that is lying on the side.
Yeah, exactly.
That one. Yeah.
I think it was
unfortunately, I wasn't there. In Ramesseum, but yeah, I saw it.
I think it's around 1,000 tons.
Mm-hmm. It will be again very interesting to reconstruct it and estimate the volume and the size. Okay, so using this reconstruction from Memphis, it was possible to transform it, rescale it to the hand from Karnak, and this is a rough estimate of the size of the original statue.
Wow.
It was 21.5 meters high from the feet. Yeah.
From the pedestal,
from the pedestal. So even for the Colosseum of Memnon, I think the pedestals they are very, very huge. They are 2 meters above ground, and another 2 meters are below ground. I think
the Colosseum of Memnon are 700 tons or something like
that. Even more, around 800 or so.
Each.
Yeah. Well, and if we recompute it, again, we will get to 443 tons. Without the pedestal would be another 100 tons, so 540 tons for the statue, which is approximately 73 elephants or one Boeing 747. So, it is possible to calculate these values. We can
gadgets,
we can stay with the crowns because it was a lot said about the high symmetry of these crowns, and again, very nice task for photogrammetry. You can generate a very detailed 3D model, and what you can do is that you flip the 3D model inside Cloud Compare or other software solution, and you compare the original version with the mirrored or flipped version, and you can calculate the deviations. It's pretty simple.
Similar to the thing that Krisdan did with the Ramesses heads, but not on 2D, but in 3D.
Yes, exactly, without any kind of distortions and projective deviations. Well, these are the results. So the object is approximately...
The scale is in millimeters?
The scale is in... in meters.
Meters.
It is in meters. And the deviations are pretty high for 80 centimeters object or 1 meter in height object. And there are deviations up to 1 centimeter, even higher.
Which one is this on the left side? Is it?
It's this one.
Yeah. It's also in the Karnak? Or it's in Luxor Temple?
This is in Luxor Temple.
Okay.
Both of them are in Luxor Temple. And you can see that, just for explanation, this looks like it is symmetrical, but it is actually not, because these blue parts mean that the compared model is 1 centimeter under the original model, the reference model, and these red parts mean that the compared model is 1 centimeter above the reference model. So it is definitely not symmetrical. If it would be symmetrical, everything would be green, in green color. And the same is for the second one.
But this is only account for vertical symmetry.
Vertical, I tested vertical symmetry, but there was nothing else to test. Because there was no exact circular or ellipsoidal or other...
We can see circularity on this.
But
maybe the next project.
Okay. So at least in 3D, we can see that there are deviations, that they are not very symmetrical.
But the other one was much better.
Yeah, it was much better, but not everywhere. And some parts of it were missing. So...
5 millimeters.
It is maybe not visible for a human eye, So they were they look very nice. They are very polished. They look perfect for naked eye, but if you perform the analysis, they are not that perfect. This is the Ramesses head, the Ramesses II head from the Ramesseum. And again, unfortunately, I wasn't able to visit the Ramesseum when I was there, but
this is just a small head. It's not the big, huge statue which we talked about. It's not the 1,000 tons. It's just a smaller one.
This is a smaller one. This is very similar to one that was on the ground in the Luxor Temple, which was then used for the reconstruction of one of the statues that is standing near the entrance to Luxor Temple. It's like the one that Chris Dunn was using for his analysis. I was trying to find it.
It's already on the top of
it is
statues.
Reconstructed. I was so pissed off.
Because that's an intact, this is repaired, this is not, I'm not sure if it's the same style either, like the one that Chris has analyzed.
I think it is.
Okay. So you compared the 3 different sources, 3 different scans?
Yes, it was actually a test. What can we achieve using social networks? It was something like a challenge that people can get a lot of interesting data, and within 24 hours I suddenly had not only this video from Johanna James from the Funny Old World channel, but also the Luma AI and the LiDAR scan from Adam and from you. And here is the Ramesseum, and here is the head placed within the Ramesseum.
Yeah.
And from this 3D model, it was possible again to create this mirrored version of the model and to compare the original and the mirrored version. And I did it for all the 3 sources of data, and we can see that the resolution is maybe different. The worst results were from the LiDAR from iPhone, but and the sharpest ones were from Johanna's video, and the Luma AI is somewhere in the middle. But
it's
I'm
a
really
decent scan.
It's pretty decent. I'm not sure what kind of footage is used for the Luma AI processing. Is it static images or 4K video?
I did the static images there because I defined the object and I went around and it took from every single direction one image. It was a guided scan, so I see where the overlap was.
Yes. Okay, well...
It's not that bad, actually.
What do you mean?
That was the same issue with the Serapeum box and Chris Dunn's measurement, that the guys who tried to kind of debunk his measurement, they were not scanning or inspecting the same object. And I think this is not bad. I'm not sure how would it look like with that original statue. It would be very interesting to scan that one.
I would love to see it, definitely, but unfortunately it is not available. But you can see... wait, one more thing. The scale here is from -1 to 1 centimeter, but that doesn't mean that the maximum deviations were 1 centimeter.
Okay, so it's saturated.
It's only for the colorization. These red parts or blue parts mean that there were at least 1 centimeter deviations or more.
But in depth. So would you see these on Chris's investigation when he flipped these images over? Would these be visible on those images?
That's a good question. Well,
because I think he measured horizontal deviation, and here this is a vertical deviation.
Yes, that's right. That's depth, right. Yeah. And there is also a lot of damage on this one, but these parts here are definitely not damaged.
Yeah,
and
the eyes are.
The eyes are too nice. Pretty nice, and still the deviations are there. What I think is not very reliable for the analysis that Chris Dunn has done is that he did not use orthographically reprojected, orthorectified images. There were some perspective distortions too. So it would be better to perform this kind of analysis if you are looking for the horizontal deviations. It would be more reliable to generate a 3D model with texture and create an orthogonal projection of it, like orthophotomosaic, and then perform the same analysis that he has done. Because if you are comparing only one photo that was approximately taken from the front, there can be some distortions always.
But here, if you look at the edge of the mouth and the eyebrows, horizontally they are very, very symmetrical, and I suspect that you would not see these depth deviations on the 2D images overlaid on each other.
Of course, yes, that's logical.
And also the face, I mean, this is
a completely different type of data.
This is I think this is remarkable, because you see that the cheeks are almost green.
They are. Yeah. It looks very nice. You can see even here that the eyebrows are slightly like shifted. They are not symmetrical in vertical direction. But who knows, maybe he really looked like that. we don't know. Who knows?
The mouse is spectacular.
Yeah. Very detailed.
Interesting.
Okay. Well, Serapeum box. It's the number 22. I'm not sure now.
I don't know exactly.
I think it was 22.
Probably.
According to which numbering?
Yeah. No
Never
idea.
mind. It's the last one on the right.
With the famous inscriptions, crude inscriptions.
Yeah, and it is accessible for the public. So again, I took a lot of images. You can see it here. The space around it was very, very narrow. It was quite complicated. I think I took more than 100 images. You took more than 400 images.
Kyle,
right?
Kyle
did it.
So yeah, probably.
Yeah. So
is it also including that data we collected?
No,
or
this is only from my data from 2022. Well, since there are many reflections on the walls, I decided to analyze only this one because it was better accessible than other walls. Because of the reflections, there was a lot of noise in the point cloud and in the 3D model. And I fitted a perfect surface on a regression plane on the surface and calculated the deviations. And here we can see that, it is not perfectly flat. The deviations are in a range between 5, plus minus 5 millimeters. How is it wide? Is it 2.3 meters?
I don't think so.
I think it was 2.3 meters. No?
I don't remember.
Definitely
2 meters seems a little bit
2 meters high and 3.9 meters long. I think it was definitely 2 and more meters wide. I would have to look for it.
It was a long time ago.
It was a long time ago.
Remember?
Definitely, yeah. So it was heavily damaged.
So basically, you fitted a plane,
a regression plane, best fit plane on this surface. I wasn't counting this damaged part in the fitting process. It would. It wouldn't be reliable.
And you were looking for
deviations,
deviations
surface deviations from the
fitted
plane. Yeah. Actually, when I did it for your data, it was the same.
Okay.
Yeah, and you used other camera, more images. It was in another day in the year. Okay, but there is artificial lighting, so it doesn't matter. But you definitely used a different camera network configuration.
Yeah.
So definitely the photogrammetry reconstruction is something repeatable. Yes, so the repeatability of the method is very high, at least for some of the surfaces, because especially because of these artificial lights, there is a lot of reflections, and that complicated the process. So these are the results. Anyone can make their own conclusions out of it.
It's not that bad.
Yeah, it's not that bad.
Up to 5 millimeters.
Yeah, but it's not perfect. I think we would do it better now.
Probably yes, but it's still remarkable.
Yeah, it's still definitely
because it's huge.
Yes.
It's
and I don't
huge.
want to speculate how it was get there.
They are almost every time better from the inside than from the outside.
Yeah.
Have you looked at the inside of this?
Not when I was there.
Or it will be in our data.
It will be in your data. Yeah. There was also a lot of noise because there was dark, and you had to use the artificial lights. But I think it will be very, very similar to this. Maybe better.
The hieroglyphs are in this 5 millimeter deviation because the glyphs are
the depth of the glyphs.
Yeah. Because the glyphs are, they could add a lot of noise, and also
of course, but you would see them. The distribution of the noise would be according to the hieroglyphs.
Why don't we see the glyphs?
Well, because they were used as a part of the texture, and
because the glyphs are real surface deviations.
Yes, they are.
They should be visible.
But I think they are not that deep.
I think they're definitely above or deeper than 1 millimeter.
Okay, we can switch here.
I think.
Do we have a better photo? No. I would have to look at the data.
Maybe if you go for 3 sigma, then maybe they would be visible.
Maybe, yeah. Or maybe if I would change,
because you can see it on the 3D reconstruction.
Mm-hmm. Maybe if I would only change the color scale, they would be better visible, because they could disappear somewhere, and even you can use these linear paths here, yellow lines. So maybe they are hidden somewhere in the noise. And especially in these places.
It's around 1 and 2 millimeters.
Yes. So they could disappear somewhere in this spectrum. Yeah.
Well, it was very, very interesting. I think your work is one of the missing pieces from these historical investigations, because as we could see now that today that the photogrammetry can solve and answer a lot of problems and issues and questions. I think it's remarkable how the Aswan question could be revisited and investigated again. As you said, it still needs more time, or still needs more experiments and more investigations. But I love how modern technology can answer these questions, which were not. No one really could answer those in the Victorian era or even before. So I think your work is really remarkable, and I really hope that we will see more. Are you planning on more visits to Egypt or more investigations?
Definitely, I would like to, but first I have to ask my wife.
What are the parts which you would really love to investigate? If you could go there tomorrow, well, what would be that site or place?
Yeah, well, definitely the Ramesses. Yeah, there are a lot of statues that need to be reconstructed and analyzed. I would definitely love to go to Karnak again. And of course, to Giza and to some of the objects that are there, the Osiris shaft or other objects. Yeah, definitely. There are plenty of them.
So where can the audience find you if they want to see your work or if they want to see more?
Well, they can find it on X, of course. I have an account there. And if they are more interested in regular research papers, peer-reviewed papers, they can find me on ResearchGate. Yeah, I have a profile there too.
I hope we will talk soon again, and obviously we will work together. We will continue to work together as well. But it was a nice pleasure. Thank you, Marián. It was a great conversation. And we have questions for the patrons. So we will say hi to the audience and then we will come back for the questions. Thank you.
Thank you. Bye.
Hey guys, before you go, I just wanted to let you know that we had a Q&A session with this guest as well, as we always do. And you can find the related link in the description. And if you are a YouTube member or Patreon member, you can submit your own questions to the guests under the revealing posts where I'm telling you who is next on the show. Thank you very much for considering and see you in the next video. Cheers! A massive thank you to my incredible supporters. Your generosity fuels this journey into ancient technology, keeping this show alive and pushing my research further than ever. As the ancient Egyptians would say, Ankh Vejasenem.